Thank you very much. I thought that my presentation was going to be provocative, but after Ladyman talk, I'm very happy that, so thank you, James, for paving the way. Okay, the title of my presentation is actually a question. I don't have a definite answer to that question, so I want to discuss possible conclusion and possible drawing. I will do my best to convince you that there is a huge problem when we want to give an answer from philosophy of time and from philosophy of physics to this kind of question. Okay? So this presentation will be about, first of all, the philosophical problem of the arrow of time. You know that it's a very famous and very slippery problem in the field. Then I will focus on the concept of time reversal. There is a widely extended tradition supporting the idea that time reversal is quite informative for the discussion. Okay? And okay, I will address the problem of the arrow of time and the notion of time reversal in non-relativistic quantum mechanics. So I'd like to start with some quotes to set the background. This is the Price book, very famous book in the field. He says, to a very large extent, then, the laws of physics seem to be blind to the direction of time. They satisfy T symmetry, as we may say. The second quote is by Paul Orwich. He says, once a genuine instance of nomological irreversibility, there is non-time reversal, has been identified, it's not hard to justify the inference that time is anisotropic. He's linking the idea of the arrow of time with the idea of time reversal invariance. He continues, there have been emerged no compelling reason to adopt time asymmetric laws. And I like this Rowley question because he uses a strange word. He says, a survey of the fundamental dynamical law of physics shows that despite the seemingly universal and directional nature of all observed processes, these laws have no mathematically preferred time direction. All are time reversal invariant. So some claims as background. First of all, so far we have that the notion of time reversal and its related symmetry seems to be quite informative as to the direction of time. Then we know that invariance under time reversal is invariance under a time reversal operator. That's the usual way that physicists represent the idea of going backward in time, or the idea of inverting the direction of time. And there seems to be a kind of conventional wisdom on the matter. And this wisdom says all our fundamental physical laws are time reversal invariant. That is invariant under a given time reversal operator. So they don't pick up a privileged direction of time. So, aims of the talk. First, to briefly analyze the problem of the arrow of time in non-relativistic quantum mechanics, focus on whether the Schrodinger equation is time reversal invariant. I will focus on Schrodinger equation. I won't consider theory interpretation-dependent laws, for example, collapse or things like that. I will focus on Schrodinger equation. And then I don't know if it's controversial or not. We will discuss this point later. But the second point is to show that the notion of time reversal has been understood in very different ways by many philosophers and physicists, mainly in quantum mechanics.
I'm sorry, I know you stare at the microphone. I just have to say something about folk wisdom. The weak force violates time reversal symmetry.
Okay, but don't worry. Yeah, I will address this point later. Don't worry. This is about Schrodinger equation mainly. And so I think that this fact, the idea that there are very different ways, two different ways of understanding time reversal in quantum mechanics, but I will claim that in general, steer the discussion towards somehow contradictory conclusion in the discussion about the problem of the arrow of time. So, outline of the talk. going to the first point, this is the general way that philosophers of time understand what is time reversal invariance. Okay? When you open up a book about philosophy of time, about the problem of the arrow of time, philosophers of time usually bring up this kind of explanation. Okay? This define time reversal in general. So, as generally understood, time reversal is a transformation acting upon a physical law by means of a time reversal operator. Okay? Main T. Time reversal invariance is a property of physical laws that represented by equation. So it's usually claimed that if a physical law is time reversal invariant, then if E is a solution of the law, the temporary Mario solution is also a solution of the law. So in this sense, we can say that as a consequence, a time reversal invariant law has temporally Mario solution. You have one solution going to the future in this way, and you have the reflection of this solution. And this is a very nice example raised by Hugh Price. It's inspired by Hugh Price. He says, imagine that physical laws are like factories. And if you have a law that is time reversal invariant, so this law factory will produce a solution, both kind of solution, one future-headed and the other one past-headed. But if you have non-time reversal invariant law, this law only produces solution in only one direction of time. Okay? This is the idea that Price has in mind. I think it's a very nice example to see how the idea of time reversal invariant law is related to the idea of solution future-headed or past-headed. So why time reversal invariant is so important for the problem of the arrow of time? Okay, because there is a largely extended tradition supporting the idea that the problem of the arrow of time depends on finding non-time reversal invariant law. So we can pose the problem of the arrow of time in terms of time reversal. If we have this question, are our fundamental law time reversal invariant? If we get a non-time reversal invariant law, so we will be able to define an arrow of time. This is the idea behind this assumption. But it is also assumed that time reversal invariance is a symmetry that theories may meet or not. Okay? You have to test. You have to test if the symmetry meets the theory or not. So the problem of the arrow of time is somehow the search for an answer to that question. Give me a theory, give me an operator, and I will say you see if the theory is time reversal invariant or not. So going to the second point, what is the problem of the arrow of time in these terms? In non-relativistic quantum mechanics, as I said before, I will set aside interpretation-dependent laws, lab collapse, so I will focus on whether the Schrodinger equation is time reversal invariant or not. And according to most philosophers of time, of the usual way to proceed, how could we come to know that? First, take the dynamic equation of the theory, then apply the time reversal operator. I don't know why, I don't know which one, so take one and apply on the dynamic equation. And what did you get? If the time reversal equation is not equal to the original one, then the physical law, and that's the theory, is non-time reversal invariant. And it's also usually assumed that the time reversal equation leads to physically impossible evolution. For example, it's one way in which we can get a non-time reversal invariant law. And otherwise, the theory is T-invariant. So this is a kind of game. Okay? This is the game of the arrow of time. You have to take an equation, take an operator, test if the theory is symmetric under some operator. So there is a standard approach. This is a widely extended approach in quantum mechanics. Most textbooks and most physicists are completely happy with this idea. You take the Schrodinger equation, you take a time reversal operator, and you get that the equation is completely symmetric under this operator. Okay? So when you open up textbooks, physics textbooks, or textbooks about quantum mechanics or foundation quantum mechanics, you get this conclusion, and they explain that you have to use an operator that is defined in this way. We call it T star operator. This is an unitary operator that reverses time, but is an anti-unitary operator also that take the complex conjugation. Okay, and this operator also includes a special rule for momentum because I will say more after, but include a special rule for momentum. For some Valentine says that you have to introduce by definition of time reversal operator a clause by momentum. Okay, so this is the standard approach. Schrodinger equation is T star invariant. Then it's time reversal invariant. Everybody is very happy with this result. Okay. But now we are getting to the dark side of the talk. There is a third approach. And this approach reached this conclusion. Okay? Schrodinger equation is no T invariant, this operator, thereby is no time reversal invariant. Okay? Because it's a orthodox approach, because some people, mainly philosophers of time, support the idea that you have to use an unitary operator that's just revert the direction of time. Okay? And this operator is defined in this way, T by minus T, and flips all the magnitudes defined in function of T. Okay, so far we have two different results. One concept, that's the general concept of time reversal, and we have two different operators. We call the thesis supporting but overwhelming majority of physics, philosophy of physics, and physics textbooks of thesis A. And this thesis, the thesis B, is mainly supported by Callender and by Albert in this article and in this paper and in this book. I'm not particularly engaged with a particular thesis, just so laying out what is the landscape. So first analysis, we have the A thesis. Schrodinger equation is evidently time reversal invariant. B thesis is the Schrodinger equation is evidently not time reversal invariant. We can raise one question: is do they contradict each other? Well, then they don't, in as much as they're relying on different operators. Or to put it another way, they understand time reversal differently. So what we should say is that if the A thesis claim that the Schrodinger equation is evidently T star invariant, and B thesis claim that the Schrodinger equation is evidently non-T invariant. Okay, arguments and counter-arguments. Why is the B thesis, widely supposed to be deeply misguided? Okay, when you say something like that, people usually say this is a very, very, very bad way to proceed. And I try to reconstruct the argument behind the A thesis, arguing against the B thesis, and it's something like that. First, it's a reductio ad absurdum. Suppose that the operator T, that is supported by the A thesis, satisfies the formal requirements for reversal and temporal order in quantum mechanics that can be used to perform time reversal. This is the first assumption. We have two premises. It's like a principle. I don't know how to call them. The energy of the time reversal system must be the same as that of the original one, that is within the positive spectrum. And T should flip the sign of P. But if we take this operator, we have that the energy spectrum of the time reversal system may be negative and unbounded from below, so bad. Furthermore, T doesn't change the sign of P, the momentum in quantum mechanics. So like T violate 2 and 3, we have to dismiss T as a genuine time reversal operator. The main premises are those the 2 and 3. So I will dig into these two premises. Why people bring up these premises? Because I think that T star, T star is the usual way to proceed in quantum mechanics, is the only operator that produces a wave function moving backward in time. You know that. Yeah, and this result, in some way, is mimicking classical mechanics. Okay, you have a similar result. What is the point? The point is that, I'm sorry, T doesn't produce a physical evolution moving backward in time, thus it fails to represent a time reversal motion. So I think that the question in this point for disregarding the operator is, why should we take it seriously as a time reversal operator since it does not actually produce a time reverse motion? To put it differently, T turns a solution into a non-solution, and what we need is a time reversal operator that turns solution into solutions. So, but okay, this is the argument for the argument for the A thesis against the B thesis. But I think that people holding B thesis can respond something like that. Okay, there's a fact that T star is a symmetry of a theory. Okay, it's a well-studied symmetry of the quantum mechanics, and I think that people don't have any problem with that. It's okay. The point is, the issue is T star symmetry informative with respect to the philosophical problem of the arrow of time? And I think that the intuition lying behind this remark is that if we take T star as our time reversal operator, and at the same time we hold that T star is informative with respect to the arrow of time, in some sense, I think that we are assuming that Schrödinger equation is time reversal invariant from the very outset. The other premises is this one, referring to momentum. Again, people say time reversal should flip the sign of P. And my question is, why should it? And I think, again, that the intuition is that in Hamiltonian classical mechanics, T flips the sign of P. Therefore, all well-behaved time reversal operator should also flip the sign of P. And it is physically intuitive that momentum flips under time reversal. So obviously, it sounds like a genuine demand for a time reversal operator that flips the sign of P. Again, a potential answer, and this answer is inspired by Craig Callender. I think he has put this answer for this question. T, time reversal, is supposed to change only the direction of time and all magnitudes defining function of time. And the reason why the sign of momentum changed in classical mechanics is because it's defining function of time. So it's very intuitive that we have to change the sign of momentum in classical mechanics because it's defining function of time. But the question is, in quantum mechanics, momentum is defined as a space derivative. So why should it change under time reversal? I think that Kellner is thinking that we need further arguments to support the idea that momentum has to change. That time reversal has to change the sign of momentum. So how this situation come up? Firstly, I think that there is a fact because it's in the literature. So there seems to be no single way to formally represent time reversal in quantum mechanics. Period. I think this is a fact. Maybe some people is deeply wrong, but some people has said things like that. And the point is that philosophers and physicists disagree on which properties are those that are relevant for a time reversal operator. So A thesis and B thesis are rivalizing because they hold different criteria for time reversal. Okay? But we can arise another point very, very, very close to the before point. And one question will be, do T and T star stand for the same symmetry? Okay? And I have found that some authors consider that T star is better described as motion reversal. Okay? For example, I'd like to quote Gibson and Polar. After defining a time reversal operator like T star, they say that under this condition, the time reversal motion of any possible motion is itself a possible motion, and we say that the equation of motion is time reversal invariant. In this approach, taking T star as our time reversal operator, we see that no metaphysical notion of reversal of the direction of the flow of time is involved. We are led to consider time reversal processes, but not reversal time itself. Although motion reversal and motion reversal invariance would be better names, we should adhere to the accepted if imprecise usage. Valentine, another famous book, is along the same line. He says, in the first place, the term time reversal is misleading. And the operation that is the subject of this section would be more accurately described as motion reversal. We shall continue to use the traditional but less accurate expression, time reversal, because it's so firmly entrenched. Finally, the last quote is Sakurai. In this section, we study another discrete symmetry operator called time reversal. This is a difficult topic for the novice, partially because the term time reversal is a misnomer, misguided misnomer, this kind of language. It reminds us of science fiction. Actually, what we do in this section can be more appropriately characterized by the term reversal of motion. Indeed, there is the terminal used by Wigner, who formulated time reversal in a very fundamental paper written in 1932. So, this is the landscape in quantum mechanics, but I like to generalize this idea because I think it's not particular to quantum mechanics, and this kind of discussion can come up in other theories and in general. So, what is the generalized version of the A thesis? I think the people supporting the A thesis using an operator like T star, first of all, is defining time reversal in a theory relative way. Okay, you cannot define time reversal in general. You can only define time reversal within a theory. Okay, a time reversal operator and a theory go together. And the very definition of time reversal does require to stipulate in which way each particular physical magnitude should behave under time reversal. For example, momentum. And I think that there is a kind of meta rule, or a meta principle that stipulates that how other magnitudes are supposed to behave under time reversal follows physically. Okay, how momentum should behave under time reversal is a physical consequence. So the idea behind this meta rule or meta principle is how should a time reversal operator look like in order to represent a physically backward motion. And I like this quote by Arrhenius and Hilary Greaves. They say, next, let us consider the electric. These guys are discussing time reversal in electromagnetism, but I think it's the same problem in some sense. Next, let us consider the electric and magnetic fields. How do they transform under time reversal? Well, the standard procedure is simply to assume that classical electromagnetism is invariant under time reversal. Okay, this is the starting point. From this assumption, we can figure out how other magnitudes will behave under time reversal. We can also generalize the B thesis, and the B thesis is supporting very, very, very different claims about how time reversal should be defined in a general way. First of all, people supporting thesis like B, or supporting that thesis like B generalized, is that a time reversal operator should be defined in a general and theory-independent way. I could, in principle, define a time reversal operator in general, and then I should look at a specific theory and look at how this theory behaves under this time reversal operator. The second point is that the very definition of time reversal does not require to stipulate in which way a particular physical magnitude should behave under time reversal. I don't need to a particular rule for momentum because time reversal doesn't care about momentum. Right? Okay, yeah. And the meta rule, remember that we have this meta rule referring to how other magnitudes behave under time reversal false physically. But I think that people supporting a B thesis or a time reversal operator defined in a general way is also thinking that how other magnitudes are supposed to behave under time reversal follows logically, mathematically. For example, calendar. Calendar is quite clear about that. Is give me an operator, and I will say you how other magnitudes behaves under time reversal logically. Logically from where? Well, okay, so if the magnitude is defined in function of time. And I like also this North quote. He says, the view of time reversal, a kind time reversal view, repeat the B thesis, is natural for a very simple reason. What is a time reversal transformation? Just a flipping of the direction of time. Okay? That is all there is to a transformation that changes how things are with respect to time. Change the direction of time itself. That's all. You don't have to. You have to add a particular rule for momentum. You have to add particular conditions. Blah blah. And finally, I'd like to raise some general question. I think this is very important to find a way to define a time reversal operator in general to address the problem of the error of time in philosophy of time, in physics, and in metaphysics. First of all, we have to decide if time reversal is equal to motion reversal. Okay. Second, we should figure out how different magnitudes flip under time reversal. There is no clear stance about that. Some people say that other magnitudes should behave under time reversal logically. Other people say the opposite. Blah blah blah. Other point is, may a time reversal operator be defined in general? May a symmetry be defined theory independently? I think that people supporting the A thesis, I mean the standard approach, is thinking that a time reversal operator should be defined theory independently. Okay, you should define the time reversal operator within a specific theory. Otherwise, it's completely nonsense to define a general time reversal operator. And I think that there is a kind of battle between two different stances. The first one is addressing the idea that a time reversal operator has to be defined practice-based. Okay, look at how physicists work with time reversal and take this operator. But other people like North or like Calendar or like, I don't know, maybe David Albert, is arguing for a purer approach. You have to get a clear understanding what time reversal means in general, and then you have to test if your physical theory are time reversal invariant or not. See, I mean, yeah, thank you.
Questions? Thanks very much. Can you say, because it's not at all obvious why changing t to minus t is the same thing as reversing time. So,
You mean in which way? In which approach? In the, for example, North approach or?
just in general, I mean, on the face of it, it doesn't. I just want to hear what you have to say about that question, because on the face of it, it doesn't seem like. I mean, it seems like I'm just reparametrizing time. I'm not changing. I'm not reversing the direction of time. I'm just changing. I'm changing.
Do you think that this is what?
On the face of it, if I change t to minus t, I'm just reparametrizing. I'm not reversing a direction. I mean, right. I mean, what I want to understand is just. I know that we all learn this, and I know there's an argument for it, but I just want to hear what you have to say about why changing a number
Yeah, okay,
to a negative number has got anything
Yeah, I get it,
to
I
do
get
with
it. Yeah,
reversing the direction of time, because on the face of it...
Yeah,
it
that's a
doesn't.
very good, yeah. I just say that I can reconstruct this presentation as an argument against present this idea. The idea to take that time reversal is in some sense informative with respect to the direction of time, or in some sense is informative with to reverse the time. I think, for example, in the north approach, that is the most clear that you have to only change t by minus t is assuming a kind of substantialist approach to time. So the thing is that you have to change the space-time structure in some sense. No, if you do that, you are in some sense reversing the direction of time. Also, I think that the intuition behind this idea is that if you in classical mechanics invert the direction of time, if you make t by minus t, you get the evolution going in reverse. But it's motion reverse. Why you call time reversal? It's not clear for me, and I think this is a very good argument against the standard approach in philosophy of time that largely thinks that time reversal and make t by minus t is informative with respect to the direction of time, or is in some sense shedding some light on the idea of reverse time. I don't know. I think that yes, I think they partially agree what you are saying, but.
You started the talk mentioning this, but then in the end, it looks for me that all these questions which you put in the end are not interesting. It's a technical question,
Yeah.
and the physical question: if there is a physical theory of nature allows reversal of motion, properly mathematically defined, then the question it might allow this or might not allow this. And then the question is it relevant for error of time? It's the problem of error of time. It's not obvious at all. It may be that reversal is allowed, and we can explain the error of time by initial condition, by any other kind of things. Or maybe we need that the nature does not have reversal of motion, and this is explanation of error of time. Connection between error of time and existence of reversal of motion in the theory, this is, I think, the deep question which should be answered. And not this technicalities, how you define this operator as operator. It's not, from my point of view, it's not very interesting.
Yeah, but for example, people discussing about the error of time in physics and philosophy of time usually don't consider initial condition or things like that because they think that these are superficial or material asymmetry in time or asymmetry in time, and they are looking for an asymmetry of time. And also it's supposed that the asymmetry of time should be reached by inverting the direction of time in your fundamental dynamical equation. That is the game. The game is take the dynamic equation and reverse the time in the dynamic equation.
So you say we need that.
This is the standard approach. This is the standard approach. For example, I have another quote here. I have many slides. I'm sorry. For example, this is John Ehrman, for example, has raised a similar point, but North, for example. The idea behind time reversal invariance and the error of time and the link between those ideas is, I think, is that. In applying any transformation to a theory, we hope to learn about the symmetry of a theory, okay? And the world that theory describes. If the theory remains the same after the transformation, it is invariant under the transformation, then it's symmetric under that operation. We conclude that the world described by the theory lacks the structure that we need to support an asymmetry under the operation. In some sense, I think that the notion of time reversal is more fundamental or more fundamental than asymmetries in time, because if you support the asymmetries in time, maybe the structure of the theory is symmetric under time reversal. So.
Sorry, John, there was Nathan wanted to make it, and then we end because we are running out of time.
But I think this conversation, and who else, if somebody else wants to do it, I think I'll share mine with you during the conversation. I think I'm talking about physicists, but. All right, well, I mean, so the T versus T star, which we've already been told maybe is not an interesting distinction by I'm very interested in as a physicist, right? Because,
Yeah.
And so that the three phenomena that immediately come to my mind that I need to understand if I'm going to make this transformation, and what I mean is I need to understand Kramer's degeneracy, which is usually explained by time reversal symmetry. I need to understand Dyson's threefold way and the necessity of an anti-unitary operator to characterize random matrices and quantum chaotic phenomena, which now has been extended to the tenfold way of topological insulators. And then I want to connect it to the Poincare transformation, right? With right. So I'm only saying this as a suggestion. If you have an infinite amount of time, there seems to be a lot of work still to do.
Okay, but all those results are. No, it's not working. Those results are a consequence of T-star symmetry, right?
I mean, it could be. I mean, the interesting point is they could be a consequence of something else, right?
The whole point is, why should we call T-star?
Yeah. No, I agree.
I am a philosopher. I am profoundly concerned with time has acceleration or not. This is my problem, and I want to get things clear. And I think that the way that you using T-star operator is something weird.
So I would love to hear your interpretation then of these things. So that's my only point. I am willing to explore other interpretations, but I'm just saying these are the ones that are the most important applications to me as a physicist.
Yeah, that's a good point. Yeah, I agree. Yeah.